Hi everybody, in this lesson we're going to put our normal distribution to work that we learned about in the previous lesson. So we're going to connect our normal curve and z-scores to solve real life problems. So quick review, a z-score is our value minus the mean over the standard deviations. How many standard deviations am I from the center, the mean? And then our normal distribution, we use normal CDF on our calculator, normal CDF, and we go low, comma, high. And that's using our z-scores there, our lower z-score all the way to our higher z-score on our normal curve. And that'll give us our proportion or our probability. So SAT scores were originally scaled so that scores within each section were approximately normally distributed. That's the key there. I'm working with an approximately normal distribution with a mean of 500 and a standard deviation of 100. So assume that scaling still applies, find the following probabilities to the nearest thousandth. That a randomly selected SAT student scores more than 700. So there's my normal curve. What goes in the center of the normal curve? The mean. The mean is 500. I want to know what is the probability that someone is bigger than 700 on their SAT score. So here's 700. I want to know what's the probability they do better than that. Well, the problem is when I go to use normal CDF, I need a z-score. 700 and 500 are great, but I need to standardize them. I need to convert them to z. So let's start by doing that. What does z equal? Well, value minus mean, 700 minus 500. In terms of the standard deviation, what's kind of my measurement? How do I measure the spread of this distribution? Well, the standard deviation is 100. 700 minus 500 is 200, divided by 100 is 2. So I'm really finding the probability that my z-score is bigger than 2. My lower bound is 2. I'm going on forever to infinity. So remember, when we're not typing in 700 into second var's normal CDF. My lower bound is not 700. My lower bound, how low do I go? Well, my z-score here is really 2. And I'm going on for forever. So my lower bound is 2. My upper bound is positive infinity because I'm going on forever. And I want to go to 3 places, so 0.023. So this probability here is 0.023. There's a 2.3% chance someone scored higher than a 700. So we can't work with SAT scores. We can work with z-scores though. Value minus the mean. How far away is 700 from 500? 200 divided by the standard deviation gives me 2. That's what we're going to be looking at in this lesson. So in 2012, the mean SAT score was 512. So there's my average. And the standard deviation was 117. For the purposes of this question, assume that the scores were normally distributed. So I'm working with a normal curve. Find the probability, rounded to the nearest thousandth, that a randomly selected SAT math student in 2012 scored between 600 and 700. So the first thing we need to do is draw a picture. What goes in the center of this distribution? The mean. I want to find the probability that their score is between 600 and 700. So here's 600 and here's 700. I want to know the probability I'm in between them. But I can't work with SAT scores. I need to convert these to z values, to z-scores. So let's do the first one. 600, how far is 600 from the mean? In terms of standard deviations. So 600, value minus mean over standard deviation. How far am I from the mean? Right, 514, I think it was. Yep. Enter, divided by the standard deviation. So 0.735. That's my z-score, 0.735. So I'm not going to work with 600. I'm going to work with 0.735. 0.735 standard deviations above average. And now for 700, z equals, well, 700 minus 514 in terms of standard deviation. So I'm going to do the same thing. 700 minus 514. How far away am I from the mean in terms of standard deviations? and I get 0.159. Shouldn't round much, but I am going to. 1.59. Yep. That's step one, is convert them to z-scores. So step one is get z-scores. Get z-scores. Now we normal CDF. Now we do our normal CDF. So I want to know, what is the probability that my z-score is between 0.735 and 1.59? What is the probability that my z-score is between these two numbers? So let's figure that out. Second distributions, normal CDF. How low do I go? 0.735. How high do I go? 1.59. Enter, 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 enter. I have a syntax error somehow because I have 2 decimal points there, my fault. And there's my probability, 0.175. So the probability that someone falls between 600 and 700 was 0.175, or about 17.5%. Get z-scores, and then use the normal CDF button to find the probability. 17.5% are between 600 and 700. In 2012, CCHS had 310 seniors. How many of these students would we expect to score between 450 and 650 on their math section of the SAT? Well, let's draw our picture. We have 514 as the mean. And I want to be between 450 and 650. So 450 is below average. 650 is above average. I want to know what proportion is between that. So step one is get z-scores. How do I get z-scores? Value. So z equals value minus mean in terms of standard deviation. I was given all this information here. So here we go, 450 minus the mean divided by how many standard deviations away am I? Negative 0.547. So I'm not really working with 450 anymore. I'm really working with negative 0.547. And now let's do it again. Z equals 650 minus 514 over 117. Let's get a z-score for that. 650 minus 514 divided by 117. And I get 1.1624. 1.1624. Let's go write that in. 1.1624. So I'm not really working with 650. I'm really working with 1.1624. The more places you go in your z-scores, the better. So I want to know this green section. What is the probability that my z-score is trapped between 0.547, negative 5.47, and 1.1624? And the way that we do that is second vars. So I'm finding the probability. That's my lower bound and that's my upper bound. Second vars, normal CDF. Lower was negative, I already forgot it, 0.547. And my upper bound is 1.1624. There we go. I can remember that one. I can't remember the first one. Enter, 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 enter. There we go. 0.5853. 0.5853. But that's not what the question was asking. The question was asking how many of these students. Well, I know what percent, 58.5% of them, of the 300. So notice I have one extra step here. How many of those kids? Well, it's 310 times 0.5853. So I need to do 310 times that probability there to see how many kids. How many kids? 181-ish is approximately 181 students. So notice I wasn't just asking for a probability. I had one extra step to multiply it by how many I actually started with. This is my probability, my proportion of this whole population here. Let's keep on practicing. Actually, I'm going to skip this problem just for the sake of time. Let's jump to 3. Maybe I'll go back to that one and do one of them. So let's read this one, but we're actually just going to do the last part. So we're going to skip this part, and we're going to skip this part for the sake of time, because video 1 was a long video. Amy specializes in the 500-meter backstroke. In competition, her mean time, so here's my average, is 39.7, and her standard deviation is 2.3. Assume that her times are normally distributed. So all the way down here to the third one. The mean was 39.7, and the standard deviation was 2.3. Yes. So all the way down here to this third one, and then we'll move on. Find the probability to the nearest thousand that Amy's time of her next race is less than 36 seconds. So step 1 is draw a picture. Draw a normal curve. We're going to try that one more time. There we go. What goes in the center? The average. Average goes in the center. And I want to know that her time is less than 36. So here's 36. I want to be smaller than that. Well, I can't work with 36. I've got to turn that into a z-score. Value minus mean in terms of standard deviations. Notice I should have a negative z-score off the bat because I'm smaller than the average. I'm below average, so that tells me right off the bat my z-score should be negative. Again, notice how I'm typing this in 2 steps. Negative 1.609. So this z-score is really negative 1.609. So I'm forgetting about 36. I'm done with that. I standardized that. I made it a z value. And I want to be smaller than that. So I'm going all the way down to negative infinity. Going all the way down to negative infinity. So I'm looking for the probability that z is less than negative 1.609. I'm going all the way down to negative infinity. That's my low. That's my high. So here we go. Second vars, normal CDF. Lower bound was negative infinity, all the way up to negative 1.609. Enter, 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 enter. And there we go. 0.0538. 0.0538, which also happens to be 5.38%. So there's a 5.38% that Amy's time in her next race is less than 36 seconds. So 39.7 is her average. There's a 5.38% chance we're smaller than 36. So again, draw a picture, find me a z-score or 2, and then use normal CDF. 2 more problems and we'll call it a lesson. Men's shirt sizes are determined by their neck size. Suppose that men's neck sizes are normally distributed with a mean of 5.7 and a standard deviation of 0.7. A manager is planning on selling 550 shirts this weekend. How many medium shirts should he order? Well, I want to be medium is what this is telling me. This is telling me I need to know how many medium shirts I have. Well, what proportion of men need a medium shirt? Well, the mean is 15.7. The standard deviation is 0.7. I want to know what's the probability that someone needs a medium shirt. What's this probability here that someone needs a medium shirt? Well, that's the probability they're between 15 and 16. What's the probability that someone's shirt size is between 15 and 16? Neck size is between 15 and 16. Well, I need a z-score. If I want to work with 15 and 16, I need z-scores. Value minus mean over standard deviation. Z equals value minus mean over standard deviation. I can do this first one in my head here. Negative 0.7 over 0.7 is negative 1. So that's actually negative 1. This one I can't do in my head. 16 minus 15.7 divided by the standard deviation is 0.4286. Z equals 0.4286. So I'm not dealing with 15 and 16 anymore. I'm dealing with these z-scores. And the probability of medium is the probability that z is trapped between negative 1 and 0.4286. That's the probability I really need to find. So I'm going to go to second distribution, normal CDF, -1, all the way to 0.4286, enter, 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 enter again, 0.5072. So the probability is 0.5072. That's the probability, but that's not the question. How many shirts should I buy? Well, there's 550 shirts being sold. 50% of them are medium, so let's find that product. There's just one extra step here of multiplying. So if I was a manager, I think I should buy 279 shirts. So 550 times 0.5072 gives me about 279 shirts should be ordered. So sometimes there's that extra step. It's not saying what's the probability, what's the proportion. It's saying how many, which involves just a quick little multiplication step once you get your normal CDF. Last one. Suppose that the duration of high school baseball games are approximately normally distributed with a mean of 105 and a standard deviation of 11. So here's 105 in the center. Find the following probability to the nearest 10,000th for places that a randomly selected high school baseball game lasts more than 2 hours. This is painful. If I have to last 2 hours of watching high school baseball. So 120 minutes or more. Well, I need a z-score. Z equals value minus mean over standard deviation. So 15 over 11 is 1.636363. So 1.36. Yeah, 1.36. So I'm not working with 120 anymore. I'm working with 1.36. That's my z-score. Does it ever stop? No, it goes on forever all the way to infinity. So what's the probability that z is bigger than 1.36? What's my probability that my z-score is bigger than 1.36? Well, here we go. What's my probability? I'm going to do second distributions, normal CDF. My low, look at your picture. How far to the left do I go? Well, I start at 1.36 and I go to infinity. 1.36 all the way to a really, really big number. That's big enough. 4 places, 0.0869. 0.0869, or about 8.69%. There's about an 8.69% chance that a high school baseball game lasts more than 120 minutes. So this is how we use the normal curve to work with real-world problems. We're given a mean and a standard deviation, and we can calculate a proportion or a probability by using the normal CDF button. So step 1, draw. You have to draw me a picture. Step 2 is get me z-scores. Get me z-values. Get me z-scores. Value minus mean over standard deviation. And then step 3 is use a little normal CDF. Use your picture to help you out. And then sometimes, this is a sometimes, use your proportion times the population. So there's not always a step 4. Sometimes you're done after normal CDF, but sometimes you have to find that product. Hopefully you feel good with the normal curve, and we'll be using it for the rest of this unit. See you guys soon.